Names and IP addresses, how do they work together? If you connect to a web server, like this one here, why do you connect to this server, for example? Well, because you found its name here from a Google search or from another document. How does your computer know how to go there? Well, the first thing that will happen is your web browser will need to first the IP address. I said before that names are in fact synonyms, or the first interpretation is names is synonyms to IP addresses. This is exactly what happens here. In order to download information from this server, having the name is not sufficient. We first need to have the address. How do we get the address? Well, we go to specialized servers that are called domain name server, DNS servers. EPFL has one, and there are a number of other ones. You will be able to try that in the lab. So this computer will send a request to this DNS server asking who is this name, and will obtain, hopefully, as answer, this address. Now, this blue address is the IP address of the web server, and when we will send an IP packet here, in the IP packet header, there will be only the address of the server and not the name. There might be the name in the text, in the application layer text that is sent, but the internet routers in the world will never use the names to forward information. This is why we will need complicated stuff called the DNS. The DNS is required because we need IP addresses here. And here, this is showing also why we need the source address in IP packets. The web server will send a response back to this user. But of course, to send the response back, you will not go to the DNS. Instead, it will use the IP address of this machine, which is sent as a source address in the packets here. So of course, you need in the DNS to have only the IP addresses of the servers. Not everyone's address needs to be in the DNS here. So this is our very first approximation of the IP layer. We will discuss many, many details of this in more details. In fact, the next module that will study in details the IP layer. But right now, this is all we will say, and that will help you get started. But immediately when we do experiments with networks, we're confronted with the MAC layer. So the MAC layer is a bit more difficult to understand, but we will try to cover that in as simple way as possible. As a first approximation, we could say that the MAC layer is an interconnection of a small number of devices without any configuration. MAC stands for medium access control. Medium access control means how you access a physical channel. For example, the Wi-Fi in this room. We're all on Wi-Fi, probably here. And how are we able to access the same Wi-Fi antenna? Then you need some arbitration mechanism, and that is what MAC stands for. So a good example of MAC is a Wi-Fi network here. That is shown here. Another example of MAC is when you connect multiple devices through an Ethernet switch. Historically, this was the network. When the internet was created in the 70s, networks were like this. You had Ethernet or token ring or other kind of equipment, and that was the network. Computers were very expensive equipment. The university had 1, 2, 3, perhaps 10 computers, and interconnecting them was done by Ethernet or cables or predecessors of Ethernet cables here. And that was the network. And the IP, the TCP IP, in fact, emerged as a mechanism to interconnect campus networks. So the name of IP stands for the Internetwork Protocol. A network being a LAN, a MAC layer network, and the internet being the interconnection of those. Things have been reversed. Since now, the IP is really the interconnection mechanism, is the network. But the low-level MAC networks continue to exist, and we'll come back to them in a second. The thing that's important to remember is that when you interconnect those 4 devices to an Ethernet switch, you just connect them physically, and you do nothing else. Right? So there is no configuration information for them to be interconnected as a LAN. But if you want IP to work, which probably you will because there are not many applications that run without IP, if you want IP to run, you will need to do configuration. So the network layer needs to have configuration with the addresses in particular. The MAC layer does not. That's a main difference. It exists in multiple versions, and we will see how we can interconnect them together. It uses also addresses that were originally, and are still today to a large extent, hardware numbers. If I connect to an Ethernet switch, I have an Ethernet card somewhere in my PC, or I have a USB adapter to which I connect a USB to Ethernet adapter, and the USB to Ethernet adapter will have an Ethernet number, which is called the MAC address here. When you connect to Wi-Fi, your Wi-Fi adapter has a MAC address here. So the MAC address, unlike the IP address, is really the serial number of your adapter. It's like if you have a bicycle, there is probably a number written on the frame of the bicycle. It's the same for the MAC address. So it identifies your adapter, but other than saying this is this number, it doesn't give any meaning. In particular, by watching a MAC address, you don't know whether the system is here in this room or is somewhere in Japan, for example. There's no way to know. The only thing you can get from a MAC address is who gave the address. So first, by analyzing the MAC address, we can know who the manufacturer is. So when in the lab, we will use Wireshark to observe addresses. Some Wireshark versions could give you, for example, the information, this is an Apple MAC address, because this is an address that has been given by Apple. But that's the only thing it can give here. The idea of the MAC address is that originally the MAC layer was like Wi-Fi, even on Ethernet. It was like Wi-Fi. What is special about Wi-Fi is that when A talks to B, in fact, the packet is broadcast. It's sent to the base station, and the base station sends it back. So if one of you talks to someone else in this room, the packet will be sent to all devices. All of your devices in the room are able to decode it. In principle, if you're not a sniffer or a spy, you don't decode the packets that are not for you. So your adapter will, so when A sends to B, for example, then it will have as a destination address the address of the adapter that needs to receive it. And in principle, the hardware of your devices will see, oh, this is not my destination address, I will not copy it. That is what you normally do. But of course, you can have what is called a packet sniffer that is configured to copy everything. Then it will be able to observe all the packets that are on Wi-Fi. So that's, of course, one of the security problems of this, is that if this guy is malicious and copies everything, and if you send a password in the clear, for example, it will be visible by everybody. So it's very easy to sniff packets at the MAC layer. With some terminology, a LAN, local area network, means a set of devices that are connected at the MAC layer. That means they are connected by a Wi-Fi station, a switch, or other interconnection mechanism that we'll discuss a bit later. So here, for example, I have one Wi-Fi LAN, one Ethernet LAN, and normally, the normal use case, but not the only one, we will see another one with bridges, that's very different. Normally, we use a router to interconnect multiple LANs, and the router runs IP. This is the historical thing I said before here. In order to work in this way, for example, if a machine here sends a packet to that machine here, it must be configured with this information of the router. That's the ugly thing about IP. IP requires some configuration information. If I have to send some information to the rest of the world, I can send it by knowing a MAC address, and then the switch will broadcast it to everyone, or the Wi-Fi base station. But how do I know if I have a machine to send from this PC to this device here? In order to send it locally in my LAN, I need to make sure that the packet will be sent to the router. If I'm sending information to a web server, there's no information in the web server address that says what's the IP address of the router. So we must configure the IP address of the next router. It's called the default gateway. That's one of the configurations that we will need to do in the lab. We'll talk again about this, but this is the first example here. Another thing we will need to know is what is the subnetwork that we are in. I gave examples here with two LANs, and now if A talks to B, there are two possible cases. If B is in the same LAN, I can send it directly to B by knowing the MAC address of B, and the Ethernet switch or the Wi-Fi will broadcast it to that machine that will receive it. But if it is not in the LAN, that will not work. I need to send it to the router. So I need to know whether a destination IP address is in the same LAN as me. This is how IP works. Any IP system needs to be able to decide this. In fact, the IP algorithm, we'll discover in detail a bit later, I'm giving some forward highlight here. The IP algorithm does exactly this. When I have a destination IP address, the first thing I see is it in the same LAN as me? If so, I send it by finding the MAC address of the destination. Otherwise, I need to go to my routing information, and hopefully I have a default gateway or something like this that I will send it to. How do I know if a destination system is in the same LAN as me? Well, by analyzing the network prefix. Every IP machine must have an IP address, plus it must know out of the bits of the IP address, what are the bits that constitute the network prefix, which is also called the subnet prefix. LAN and subnet is the same. Subnet is what IP views, LAN is what physically we view here. They are synonyms for us here. In order to know the subnet, we need to configure the number of bits, because this is not a standard. For example, at EPFL, for IPv4, the subnet prefix is 24 bits. The IPv4 address is 32 bits, 4 words of 8 bits each. So the prefix at EPFL is the first 3 words here. So, for example, 128.178.71, I know that this is the prefix here. And you can observe here that all addresses on these diagrams that are on the same LAN here, they coincide. Their third word here is the same here. So the prefix is made of 24 bits. Right? If we would do this today, and you have to express the fact that the prefix length is 24 bits, then you would put a box somewhere in the configuration saying prefix length equal 24. Unfortunately, this is done using historically, this is not the way it was done. They used a much more clumsy way, which is called a network mask. So instead of saying that the prefix is 24 bits, you will say the mask is 255 3 times .0 here, which is a very cumbersome way, a hacker's way, if you want, of saying 24, because if you write this in binary, you obtain this. Right? You obtain a long string of ones. 255 is a word of 8 bits equal to 1. So 3 times 8 bits equal to 1 gives 24. So a mask is often used in IPv4, practically always, practically never with IPv6, as a way to indicate the length of the prefix. So in IPv6, we would typically say /64, for example, to mean the first 64 bits of this long representation here. We could say it with /24, but for historical reason, and since people don't understand why they do things, most people repeat the old complicated stuff, and they will say that instead. So you will have to work with that. We'll come back to that. Sometimes we need a calculator, a programmer's calculator to map the ones to the zeros. In particular, if you have weird things like our ETH colleagues found it necessary or smart to use 26 bits, right? As long as the prefix is a multiple of 8 bits, things are very simple. When it's 26, of course, it's much more complicated here, right? So the mask will be some very weird thing here. We'll come back to that in detail. Right now, the thing that's important is how the things fit together. Here I'm showing 2 LANs that are connected by a router here. A router is something that interconnects 2 LANs. Here I'm showing also a switch. A switch is something that interconnects typically physical wires, but can also interconnect wireless stuff. And the first thing we need to remember is that a switch is inside a LAN. If all those devices are interconnected by the switch, they are in the same LAN. It is the same thing as if they would be connected via a Wi-Fi antenna. So switches, also called bridges, are inside a LAN. We'll come back to that in detail. We'll see how bridges work, which algorithms they need, etc. But right now, we should remember that this is one LAN, this is another one, and we have two LANs because I've put a router in between. If I had put a bridge here or a switch between the two, I would have one big LAN. But here I have two LANs here. Now assume the web server sends a file to Elaine. Elaine is that device here. So assume I have a file that goes here, and now I will observe the packets at different places here. I will observe the packets as it is sent by the web server, as it is seen at the bridge that is here, or which is a switch. Switch and bridge are synonyms, at least today. So we will observe the packet at the source, at the bridge, at the router, and at the destination. Observing packets is one of the things you will learn to do in Lab 0, in the very first lab. So the application layer program will probably use a number of object libraries and classes and all a zoo of things to make its job, but at the bottom part of it, it will call the transport layer, and it will probably use TCP if it's using HTTP, and it will do something like send. S2 is the name of the socket. We will see what the socket is, but essentially this is associated with a port number. It means in which port number I'm using when I'm sending this information, and a block of information. The data block may be a response to the request that was sent by Elaine. It may be cryptographic material that is required for the transmission, or it may be the video or the image that has been requested, whatever needs to be transmitted here. So this is the interface between application and transport layer. It's called a service interface. Service interface is the interface between two layers. The transport layer gives a service to the application layer. Any layer gives a service to the layer above. The service interface of the transport layer is called the socket interface. In practice, that's the only interface that we will use. You use an interface like this, or you use other interface only if you're developing the Linux kernel, for example. But in user space, that's the only interface we will see. Then between the transport and the network layer, there is an interface inside the Linux kernel, for example, that uses this data block and makes as many packets as is necessary. A large data block will require more packets. So it will pass that to the network, which is the IP layer. And the IP layer will deliver that to the Ethernet adapter. Now the IP layer will add all the IP headers, all the information that is required for being able to deliver those IP packets. Essentially the IP destination address of Elaine, but also the source address here of this machine. In the transport blocks here, of course, there are things I haven't shown. There are, for example, port numbers that are not part of the data block here. Then, as those packets are passed to the Ethernet adapter, they are transformed into Ethernet packets. So we see that at every time we have an encapsulation, we simply take the data of the layer above and we add to it. We add what? Here we add what is called a MAC header that contains in particular the MAC address of the destination. What is the destination here? Well, we are sending the information from the IP viewpoint. To whom are we sending the information? Well, to the next IP system, which is the router. So the MAC address here will be the MAC address of the router, not of the bridge, of the router. Now, the physical cable will connect to a bridge. The bridge analyzes the MAC address. A bridge is a MAC layer stuff, so it looks only at the MAC addresses here. It will analyze in particular the MAC destination address, or simple bridge will only analyze the MAC destination address. It will know, oh, that's the MAC address of the router, so it will send it on its port that leads to the router. And the same packets, instead there's no modification to those packets, are delivered to the router. Now they're delivered to the MAC address of the router, which means the MAC, the Ethernet adapter of the router will receive these packets, will copy them to the operating system, and then inside the MAC packets, there are IP packets. Now they're delivered to the IP layer. The IP layer analyzes. What is the IP destination address contained in these packets? It must be the IP destination, the final, Elaine's device, not the IP address of the router. If it would be the IP address of the router, the operating system would say, oh, this is information for the router. Normally, you don't speak to the router. except when you're managing the router. For example, if you're a network manager and you're configuring a router, then you will send information to this router. But that's not the case here. So the IP destination address must be that of the final destination. The network, the IP layer at the router will do its IP layer job, which is here, it's an intermediate system. So it has a routing table. It says, oh, this is this destination address. I know where to send it. Routers must know where to send every packet. So it knows it has to send it to the left here. So it will send it. How does it send? Well, it knows, remember the router was, the router was interconnected, the wireless LAN and the Ethernet LAN. So it knows the destination is on the wireless LAN. So it now needs to send it over its wireless interface. So it will create a wireless MAC packet, which is this yellow or orange packet here, which is here. So we'll create the same IP packet, but now almost the same. One little thing has changed, but the destination IP address is always the same. And it will now create a MAC layer packet, where the MAC address is now the MAC address of Elaine's, the Wi-Fi address of Elaine's device. Then the Wi-Fi system will transport it to through Wi-Fi. The destination address is visible here, so Wi-Fi's system at Elaine will copy it, deliver it to the network layer that will check that the destination address is well an address of this system, otherwise the packet would be discarded. We'll remove the IP header, receive the transport layer blocks that contain the port numbers that we'll use to deliver it to the application. Now it will be delivered to the application when the application reads it. So typically for this type of application, it's not push, but pull. So it will be put into a buffer. And whenever the application decides to read, to consume from the buffer, it will be delivered. This is the anatomy of how the layers, in fact, work together. Here. Some terminology. A packet is called packet differently depending on where it is seen. We can always call them packet. We also call them PDU, Protocol Data Unit. If it's a TCP layer packet, it's called a segment. If it's an IP layer packet, it's called a packet. If it's a MAC layer packet, you can call it a packet, but many texts will call it a frame. That's the difference here. I used the word protocol. I said, well, IP is the Internet Protocol. What is a protocol? Well, a protocol is the rules of the game between two things that are at the same layer. For example, the network layer protocol, IP, is very simple. It simply explains what you must do when you receive an IP packet, which essentially, except if you're hacking or doing special things, means you analyze the destination address looking at your routing table and doing things that we'll discover a bit later. The transport protocol, TCP, is a bit more complicated. It says what to do. For example, what do you do if packet 3 is missing? And how do you detect that packet 3 is missing? Those are the rules of the game of TCP. TCP is an end-to-end protocol, which is shown here. There are only two entities involved in the TCP protocol, whereas IP and MAC are global. So there are multiple entities, and in particular, there are intermediate systems that are normally involved at the IP and MAC layer. In the labs, you will do Wireshark, so you will observe things. So here is how things are. We will observe a MAC header, IP header, TCP header, and TCP payload. And probably inside the TCP payload, there will be an encryption header. So this is the typical case, most common case when we will look at observations. This is how the layers are translated into encapsulations. You will discover that in the lab. So, quick question to make sure everything is well settled here. I do a packet observation at 1. Where is point 1? Point 1 is here. So we put a packet sniffer here. How do we put a packet sniffer? How do the bad guys put a packet sniffer? Well, if this is a wired system, that's very simple. You break the Ethernet, you put a switch here, and or what is called a switch that's what is called a hub, a system that will copy its input on all outputs, and then you copy everything. If it's an optical fiber, you put an optical fiber splitter that will copy the signal on 2 inputs. So that's very easy to do. And this is why all things should be encrypted that you send over the internet. So we put a packet sniffer here at point 1, so on the cable here between the router and the switch, and we observe the packet. In particular, we observe the destination MAC address and the destination IP address. What should we see? I close the poll in a few seconds. It's moving. Closing the poll. The majority says A, which is the correct answer. So the packet is sent by the web server to Elaine, so the IP address is Elaine's device address. The MAC destination address is the router's MAC address, because the MAC layer, of course, is local. Right. If you've understood this, well, you've a good point you understand how layering works, at least at the interconnection layers. Let's say a few more words on the physical layer as far as it impacts us. So the physical layer is, of course, the topic of other courses. We will not see how to encode messages over twisted pairs, for example, but it has an impact that we need to understand. So the physical layer is, of course, the thing that transforms the world, the digital world, bits and bytes, into physical signal. At the end of the day, we live in the physical world, so that must be physically transported. And practically all systems will use electromagnetic waves, either in the form of light in optical fibers, or in the form of electromagnetic waves of different frequencies on cables, or wireless here. If you go to and take a course on physical layer communication, for example, the communication course of Bixio-Rimoldi or other courses, the professor will be upset by your use of bandwidth. So what matters for us from a physical layer is what is properly called the bit rate. The bit rate of a channel is how many bits per second can be sent with the given physical layer system. On cable system, it is typically fixed. It depends on which adapter you use and how you set it up. On wireless channels, it varies. It depends on the conditions. At night, when there is less interference, the bit rate is probably a bit larger. During the day, when there's more interference from the sun and other devices, the bit rate is smaller. So the bit rate is how many bits per second we're able to send. Invariably, in practically all computer science literature, so all TCP/IP and internet literature, this is called bandwidth. Right. Bandwidth means bit rate. But bandwidth is physically something else. Bandwidth is when you do a spectral analysis of a signal, and it is related to the bit rate by information theory. For example, a very simple formula for a very simple channel says that if I know the signal to noise ratio and the bandwidth B, the capacity that can be achieved is given by this formula. And if you have good coding schemes, you will be very, very close to this capacity. So because of this, there is this confusion, so I will also use bandwidth sometimes to say bit rate. Something else that we need to be aware of, propagation versus transmission. Here is, for example, another space-time diagram where now time is flowing horizontally, and I'm showing some Ethernet short cable coding scheme that use a differential Manchester. That is a very simple coding where essentially if you have a transition going down or a transition, it codes a 0. If you have a transition going up, it codes a 1. That's a very primitive way of doing a physical layer. And the very first Ethernets use that. But the interest of this is to show very clearly two different things. So the first thing is how much time it takes to send n bits. So here I'm sending 1, 2, 3, 4, etc. n bits here. How long this transition is gives us the bit rate. If it's very short, then you can transmit more bits. So how many bits you can send is given by the length here. And you see on the horizontal axis the transmission time. It is the time to send a number of bits here. This is given by technology. It has practically no limit, or it will have quantum physics limits, but right now we can have optical fiber systems that transmit at terabits per second. Whereas when the internet started, the transmission rates were kilobits per second. One of the wonderful things is that the same TCP/IP technology was able to sustain such dramatic changes here. So the bit rates get always better. An Ethernet cable, when I was a student, was 10 megabit per second. Today it's 1 gigabit per second. But there is another thing, which is when the signal is propagated over the wires, then it propagates at the speed of light. You know that the speed of light is the same for all electromagnetic radiations, but it depends on the material. In air or open space, it is at 3 times 300,000 kilometers per second. In copper or in optical fiber, it is less here. Now, of course, this is astronomically fast. The light appears to be instantaneous, but since the internet is global, for us it is not instantaneous. For example, it takes 5 microseconds to go a kilometer. Now in 5 microseconds, a computer can do a lot of computation, and a multi-gigabit or terabit per second system can send a lot of bits. Worse, if you go around the globe, for example, if you ping New Zealand and back in optical fiber, it will take 200 milliseconds. 200 milliseconds is the time it takes for the signal of your ping and the reply to go to travel, assuming you go the shortest path, which is a long circle around the Earth. Probably you don't go the shortest path to New Zealand. You go first to some operator that has a cable somewhere, which is perhaps in Europe, perhaps in the US, and then you go perhaps to Australia and then to New Zealand, etc. So it will be worse in practice. Right? So 200 milliseconds is visible, right? This is it's visible when we talk over Zoom or audio. 200 milliseconds is just at the limit of visibility for interactive communication here. We will see that this has an impact, for example, on the design of the TCP protocol. Here are, for example, some examples of numbers. When we have very short systems, for example, in a data center where the bit rates are terabits per second, we see that the propagation times are, in fact, much larger than the transmission time. So even though the data center is small and the bit rate is very large, even though a data center is very small, the bit rate are so large that the 20-meter distance becomes large also. What does it mean when the propagation time is large? Well, the propagation time is the incompressible time. That's the thing that makes distributed system complicated. It's non-instantaneous. If I change a record, if I change a massive copy of a database and I say, do this, right? The time it takes to do this is limited by the propagation time here. Transmitting the information is very fast, but waiting until it's physically done may take some long time. So protocols for such system must always account for propagation. When we go over the internet today, is the same thing if we go very far. If we go close, then it will be different here. So when we go that far, we see that the propagation time is larger. Here, the propagation time is negligible here. So if you go to 2 kilometers or even 20 kilometers, the propagation time is not very large here. So this is over satellite type communication. But if you go with today's internet technology, propagation time are very short. If you stay local, they are long if you go global. This is, we will discuss that when we talk about TCP and its performance, for example. And this is why a lot of information is cached locally. So all information servers of big companies that are in California, for example, they have what is called content distribution network in every country of the world in order to combat the propagation time. I've mentioned propagation time, bit rate. Another thing is throughput. Throughput is the useful bit rate. So it's in the same unit as the bit rate. But usually, if I have a link at 1 gigabit per second, I will not get 1 gigabit per second of useful data through this channel. Why? We will see a number of reasons that are obvious. Overhead, when we transmit a block of data, we put it into a MAC, IP, TCP, or header. So all of these consume bits per second. They need to be transmitted. They consume data. We'll see that an IPv6 packet has much more overhead than an IPv4 packet. So it requires, it costs something. So you will never get 1 gigabit per second because of this, but also because of protocol waiting times. And what are the protocol waiting times? Here is an example. Here, this is our first example of a protocol. If you want, this is an oversimplified version of what TCP does. Remember that one of the goals of TCP is to combat packet losses, to do once for all for the programmer what needs to be done when a packet is lost. What should you do when a packet is lost? There are zillions of things we could do, but the simplest of all is to detect the loss and repeat it. So this is called the stop and go protocol. This very simple protocol does the following. I send one packet, one piece of information, and I wait for a confirmation that this packet has been received. If the packet is confirmed, I can continue and do a new job here. Here, if the packet is lost, or if the confirmation is lost, by the way, I must detect the loss. How can I detect the loss? Then the very frequent system is timeout. I wait for some time, and if nothing comes back, I think that the packet was lost. Of course, we have to be careful with timeout. Timeouts are very, very tricky things. They must always be set up appropriately. We will see how this is done in TCP, for example. Here, the timeout must be longer than the time it takes normally to receive the packet and the acknowledgement, but not much longer. If it's much longer, then when a packet is lost, we might wait a lot here. So anybody who writes an application protocol is confronted with that, will need to handle cases like this. But here, in particular, I'm assuming this very simple protocol. So packet 2 is lost here. After some timeout, I detect the loss and I transmit it again here. So this is a very simple protocol. This is what is done when, for example, you have very, very simple application where you send only one message. If you send only one message, you don't want to use TCP because, as we'll see, TCP sends at least 3 messages in order to, as overhead, in order to do anything. But if you send only one message, you will need to do this. What is the throughput of this protocol? Well, we could ask what is the throughput when there are losses, but this is a question for the performance evaluation course. We'll not do it here. But when there is no loss, so the very first regression test I do of this protocol, I mean, is this efficient? If there are losses, I can understand that when a packet is lost, I need to retransmit. Okay, certainly some performance degradation. But if there is no loss, this should not cause me too much trouble. But in fact, we see here, I'm zooming exaggeratedly on a case. I'm showing here a time-space diagram where I see what happens. I send a packet, then I need to wait. I need to wait until the packet is received and an acknowledgement comes back here. This waiting time is a loss of throughput here. While I'm waiting, I'm not sending anything. So if I compute what is the useful amount of information I'm sending through this channel, I see that from this time to that time, the useful information is the red one. That is the bits of the packet. But I need to wait for 2 things. I need to wait until the packet, the last bit is sent and until the first bit of information comes back. This is the propagation time. That's the speed of light. And then I need also to receive an acknowledgement. So that's also a waste. So if we analyze this, we see that during an interval of this duration, we can compute those durations. The time to transmit is the length of the packet divided by the bit rate, 2 times the propagation time, if it's symmetric, plus the time to receive, which is the length of the acknowledgement divided by the bit rate, here assuming the bit rate is the same in 2 directions. This is the time it takes, and how much information did I send over this time? It's capital L bits. So the throughput, because it repeats itself the same and the same again and again, you can easily see that the throughput is the bits I send divided by the time it takes to send those. And if I massage this formula, I will see the throughput here is equal to B divided by 1 plus something. So B is the bit rate, and the plus something is the inefficiency. What is the inefficiency? Well, there is the fact that there is an acknowledgement. So we send data, we receive an acknowledgement. The acknowledgement is a waste of channel capacity in the reverse direction. So, and we need to wait for it, so we pay a bit here. And the other thing here, as a name, it's called the bandwidth delay product. It is the round-trip propagation time multiplied by the bit rate divided by the length of the packet. Now, the propagation time divided by the bit rate is the size of the channel in bits. This is how many bits exist physically in the channel, are on the fly in the channels. Right? Those are the bits that are on the wires. So I pay for this inefficiency here. And if I look at all the things, the examples I gave before, when we are in situations where the propagation time is large compared to the transmission time, the efficiency of the stop-and-go protocol is very bad, is very small. So if I am in a data center and I would use this protocol to transmit information from one computer to the next, I would have a throughput of 3.8%. So you have a big file to transmit, that would not be efficient. We will need to do something smarter. So TCP will need to be smarter than that. You cannot simply send something, wait for an acknowledgement. You will need to be a bit smarter. But you can do that if you're in situations where the transmission time is dominating the propagation time. Here, there's no need to do sophisticated thing. So here's our first impact of the numbers of the physical layer. We will come back to that when we study, in particular, TCP. Voila, that's the end of this first module. We will stop here for the lecture part. Next week, we will start the very first active module of the course. We'll dive into the IP layer. I see that there are a few questions